All right, let's have a look at the infamous block sliding down an inclined plane problem. Now, I like this problem because it helps to illustrate a certain set of core skills that can be very useful for solving problems using Newton's laws of motion. Now, what we have here is a block sitting on top of a ramp that makes a 30-degree angle with the horizontal, and the block is sitting 1.5 meters from the top of the ramp. So the way to approach these problems is to first draw a mental plan, a mental path to the solution. This instance, this involves identifying the variable that we're being asked. In this case, it's the final velocity of the block at the bottom of the ramp. Now, because we're going to use Newton's laws of motion, I know that I could probably solve for the acceleration of the block down the incline. And knowing the acceleration of the block down the incline could be useful combined with the displacement and the initial velocity to solve for the final velocity. Essentially, we're looking at, once we find the acceleration, we're looking at a one-dimensional kinematics problem. Now, finding the acceleration requires a couple other steps. It requires identifying all the forces acting on the block. It requires choosing a convenient coordinate system for the forces. And by convenient, we mean a coordinate system that will help to simplify the algebra. We are going to use the forces that we identify to set up a system of equations by summing up all the forces along the x-axis and setting that equal to the mass of the block times the acceleration along the x-axis, and doing a similar thing for all the forces along the y-axis. Once we find the relevant information to solve for the acceleration of the block down the ramp, as I said earlier, it'll turn into a kinematics problem. So that is my mental path to the solution. Let's start with the free body diagram. These can be tricky, but they're essential to setting up the right system of equations. So let's start by identifying the easiest force to identify, gravity. We know gravity points towards the center of the earth, and so it's going to be pointing vertically downward, and so it's easy to draw on the block. Now, as a result of gravity pulling the block into the ramp will respond by exerting a normal force on the block, and the normal force is going to be perpendicular to this plane of the incline. And so the normal force will be slightly off of the vertical axis, and that's important. A lot of students I've noticed make the mistake of, for some reason, always assuming that the normal force has to be vertical, and that's not the case. The normal force only has to be perpendicular to the surface of contact. The surface of contact in this case is parallel to the plane of the ramp. Finally, we could have friction. Friction will act against the motion of the block, so the block will be sliding down the incline, and if there's friction, it would be opposing that direction. We choose a coordinate system that essentially simplifies or reduces the number of components that we have to calculate, x and y components. So in this case, a tilted coordinate system works best because it forces the friction vector to lie completely along the x-axis, thereby not having a y component. And at the same time, it forces the normal vector to lie completely along the y-axis, therefore not having an x component. And so the only vector that would have both an x and y component will be mg, the gravity vector. And we can find that. We can find the y component and the x component of the gravity vector if we know the angle between the gravity vector and the y-axis, or the gravity vector and the x component. A simple geometric analysis will show that the angle of the ramp is exactly the same as the angle between the gravity vector and the negative y-axis. And so knowing that the angle between the negative y-axis and the gravity vector is 30 degrees, we can write down expressions for the y component of gravity and the x component of gravity. Namely, the y component will have a magnitude of mg cosine of 30 degrees. Why? Because this is 30 degrees right here, this angle, and this leg of the right triangle is adjacent to the angle, and this leg of the right triangle is opposite to the angle, and therefore it's a sine. So it's mg hypotenuse sine of 30 degrees. So now we can write equations. We can sum the forces along the x-axis. First, we add the frictional force and we put a negative in front of it because it points in the negative x direction. And to that, we add a positive x component of the gravity vector because this vector, this component here, points along the positive x direction. Those two vectors added together should give me the mass of the block multiplied by the acceleration of the block down the incline, the x component of the acceleration down the incline. We can similarly sum forces along the y direction. Along the y direction, we have the normal force as a positive n, and then we have mg cosine of 30 degrees, or this guy right here, as a negative number because it's pointing in the negative y direction. And those two vectors along the y direction add up to give me the mass of the block times the acceleration of the block along the y direction. Now clearly this block is only going to slide down the incline and it's not going to bounce up and down. So there should be no acceleration in and out of the plane of the ramp. What that means is that this AY acceleration should be 0 because the block stays on the plane essentially. Now, the acceleration down the ramp, AX, that's the variable that we care about. So we want to solve for this variable. And right now I'm going to make an assumption to help simplify this problem. And we're going to assume that the friction is 0. It's a frictionless plane. We assume that it's a frictionless plane. We can see that we have mg sine of 30 equals to max. And so we should be able to solve for AX without knowing the mass, in fact, of the block, because you can see that the mass is on both sides of the equation, which means that the mass cancels. So the mass cancels and we're left with the acceleration down the incline being equal to g sine of 30 degrees. That's essentially 9.8 times sine of 30 degrees, and that gives me 4.9. Now, one thing to note, the masses cancel. That means the acceleration of the block down the incline is independent of the mass. And that's actually something that is consistent with the Galilean observation that acceleration due to gravity is independent of the mass of the object. So that's a good thing. We find the final velocity now at the bottom of the incline because we can use the acceleration we just found, the initial velocity and the displacement down the incline, combined with the proper kinematic equation to solve for the final velocity. We plug in chalk, we plug in the numbers for V naught, delta x, and A. We do it all in standard SI units and we get a value for the velocity squared, from which we extract the value of the velocity, 3.8 meters per second. The last check is to check if this is an intuitive answer. This is an answer that makes sense, that's reasonable. So we convert this speed to miles per hour because that's something that most people have an intuition for. At least I have a better intuition for miles per hour than meters per second. And I do that by essentially just multiplying 3.8 by 2. That's a good estimate. So what we have here is we have a speed of 8 miles per hour. So the block, after sliding down the ramp 1.5 meters, is essentially going at the speed of somebody running on a treadmill. That's pretty reasonable. So we'll keep it.